You will continue to get
Uncle Phil تبع فريش برنس اوف بيل
dynamic pressure, the dynamic
جيمس
pressure.
افري اللي
And we will start a new section today, which is on curvilinear motion, normal and tangential components. Okay, so until now we have considered motion in a rectangular frame where we have I, J, K fixed and perpendicular. Guys, please, can you mute your microphones, please, when you don't ask questions? So we have in curvilinear motion, the path of motion of the particle will be described using U and UT coordinates, which are normal and tangential to the path. What do we mean by this? So here, this coordinate will not be fixed, it will follow the particle. So if you look at the figure here, for example, you are moving along this curve. At each location, for example, here at the origin, you have that the direction that is tangent to the path is like this. So you can define UT like this here. And UN always directed towards the center of curvature. What is the center of curvature? If I am moving on my curve, I can consider that for a very small element, so like this one here, I am moving on a part of a small circle. So this is an arc of circle. So at each location, I can approximate my motion as a motion on a circle, and I can find what is the corresponding radius of this circle. So here, let's say, like this is the radius at this location, for example. At the other location here, at each location, I have a new radius of curvature. Here, for example, like this is the arc of circle I'm moving on, and this will be the radius of curvature at my corresponding location. So in UNUT, what is happening is that the frame will follow the motion of the particle, so it's not a fixed frame. Plus, we have that at each location, I have a new radius of curvature. Okay? Now, in particular, for example, circular motion is a particular case where the radius of curvature is the same everywhere. It's equal to the radius of the circle. Okay, but in general, I can have variation of the radius of curvature. So for the normal tangential coordinates, the origin of this frame always is the particle. This is why it will follow the particle. And the direction of its unit vector is defined by UT, which is along velocity because it's tangent to the path, and UN, which is perpendicular to UT and directed towards the center of curvature at the corresponding location. So as you can see here, they draw it for you. You have the center of curvature for different locations. Okay, as you can see, rho is varying with the position. So the curve can be constructed from a series of differential arc segments ds, and plane contains an anti-axis is referred to as plane.
دكتور بس قبل ما تكملي في students بالwaiting room.
Okay. Okay. So now, how to define velocity and acceleration in normal tangential coordinates? So you have that when a particle is moving along a curve and we want to use normal tangential coordinates to define its motion, first we should define the velocity vector and the acceleration vector. Okay, the velocity vector here is very easy to define. Why? Because UT will always follow the velocity. So UT is in a way that it's always tangent to the path, so it will be in the direction and of the velocity. So we can say that UT is the unit vector of V. Okay, so we can write that vector V is the magnitude of V times unit vector UT. Now, what is little bit complex here is to determine the acceleration. Why? Because here we have that A is derivative of velocity, and velocity is VUT. But the problem here, which is little bit complex, is that UT is variable. So if I want to derive VUT to find the acceleration, so A is equal to A as vector, of course, is equal to the derivative of the velocity vector, which is v magnitude times ut by dt. But here, I cannot say like in rectangular components ijk, Cartesian coordinates, that ijk are fixed. No, ut is variable, so when I derive, I should derive it also. So here it's like you have the product of two functions. So to derive, you should do first dv or by dt times ut plus v dut by dt. Okay, and what we should do now is to determine what is dut by dt to be able to determine our acceleration. Okay, now in order to know what is dut by dt, we will do a small analysis. What is dut? Okay, so if you look here at the figure, let me zoom it a little bit. So here, if we look at this figure, okay, to determine what is dut, dut is the variation of ut. So to determine dut, what I will do, I will take two positions that are close to each other. So this is ut at a certain instant, and after a small displacement d theta here, a small rotation d theta, I have a new vector ut, so I'll call it ut prime. And of course, I have, this is un for the first frame, and this is un for the second frame. And here, because I'm considering a very small displacement, that then I can consider that I am on a arc of circle. So un, the two un will intersect in the center of curvature at this instant. Okay. Now, what is dut? First, look, un and un prime are doing between them an angle of d theta. And since ut is perpendicular to un and ut prime is perpendicular to un prime, so first we can say that the angle here, the angle between un and un prime will be equal to the angle between ut and ut prime. So the angle between ut and ut prime will be equal to the angle d theta. Okay? So now if I do a clearer figure here, I can represent in this figure the two vector ut prime and show that the angle between them is d theta. Then what is dut? Dut is the change in ut, so you can draw it in very easily like this, because dut is simply the difference between dut is equal to ut prime minus ut. Okay, and here from this figure, from vectorial relation, okay, you can say then that ut plus dt, so ut plus dut will give me ut prime. So in the figure, how is dut? It's directed from ut towards ut prime. So now I determined vector dut. Okay, I still need to find its expression. What is its magnitude? What is its direction? First, for its magnitude, as you can see here, what we have here is that d theta is a very small angle, very small. So d theta is nearly equal to what? This angle is nearly equal to 0. Okay? Since this angle is nearly 0, and I have that ut and ut prime are unit vectors, so this should be, this line magnitude is equal to this one, and it's equal to 1 because ut is a unit vector. So here the magnitude is 1, and you can say that dut, okay, is equal to the length of this arc of circle, because look here we have a very small displacement. So we can say that if you want, this length dut is equal to the length of the segment arc of circle, and the arc of circle length is what? Is r times angle. You know that for an arc of circle, how you determine its length? It's radius times the angle. So we can say that the magnitude of dut, so dut magnitude is equal simply to 1 times d theta. So now we know the magnitude of dut. We still only need to find what is the direction of dut. So now to find the direction, we said that d theta is nearly 0. And we have here an isosceles triangle because this is equal to this one equal to 1. Because it's an isosceles triangle, so I can say that the angle here, the angle between ut and dut is equal to what? If this is 0 and I have an isosceles triangle, so the two angles should be equal to 180 over 2. So this angle is 90 degrees. What does this mean? So if you look back to your figures, this means that ut and dut are perpendicular. And if dut and ut are perpendicular, then as you can see on the figure, dut is directed along vector un. So now I know that dut is along un, and I know its magnitude, so I can simply say that vector dut vector is equal to the magnitude of it is d theta, and the direction of it, the unit vector of it is un. So dut is simply d theta un. Now what I want is dut by dt. So dut by dt is equal to d theta over dt times un. Now, what is d theta by dt? D theta by dt is called angular velocity, okay? Because it's the variation of the angle with respect to time. So here, to know what is d theta by dt, go back to your figure here. D theta represents the angular displacement for the circular motion, for this small circular motion here. Because we said that for a very small segment ds, we can consider that we are moving on a circle. Okay, so d theta is the circular displacement. So if you remember from school, okay, when you have circular motion, how you write your angular velocity omega? Omega represents d theta by dt, the variation of the angle, and can be written as what? As the linear velocity over what? The radius of curvature, d over rho. Okay, so we can replace in this equation, we can replace dut by dt by v over rho un. Okay, so from here we deduce here that we can replace d theta by dt by v over rho, and then the expression of dut by dt is simply v over rho times un. Now, if I replace back into my acceleration equation, what do I get? A equals to dv by dt along ut plus, we said that we have v times dut by dt. If I replace now dut by dt by its expression, it's v over rho times un. So now what do you get? Your final expression will be dv by dt ut plus v square over rho un. Okay, this is why we say in normal tangential coordinates, the velocity will have only a component along ut. However, the acceleration will have two components, one along ut, one along un. Okay, so in summary here in red, the box in red is summarizing what we did. So the acceleration in normal tangential coordinates is divided into two components. The first one is called tangential acceleration, which is the acceleration along ut, and an is called the normal acceleration. So here this is the tangential acceleration, and an is the normal acceleration. Okay, and we have that at is given by dv by dt. So if you want the tangential acceleration, which is dv by dt, represent what? It represents the change in speed. Okay, it will represent the change in speed. However, an is due to what? Why we have an here? We have an due to the change in direction. If you don't have change in direction, un will be 0. Why? Because if you don't have change in direction, then you move on a straight line. And if you move on a straight line, what is the radius of curvature? The radius of curvature for a straight line is infinity. Okay, is infinity. So if you replace here an v square over rho for a straight line is infinity, and an will be 0. So we only have an due to change in direction, okay, due to the curvature of our path. So the normal acceleration is given by v square over rho, and it's representing it's due to change in direction during motion, okay, in direction during motion. And we only have it for curvilinear motion. If you have rectilinear motion, we don't have any. Okay. And of course, once we find at and an, we can calculate the magnitude of the acceleration by doing radical of at squared plus an squared. Okay. So this is how we determine velocity and acceleration in normal tangential components. So now let us move to something else. We'll do a small problem together. Now, just before going to the problem, I want you to pay attention. We have already developed relations for constant acceleration. The relations we have developed for constant acceleration are valid here for which a? For at, an, or for the total acceleration a? Who will tell me?
For at.
Very good. Why for at?
Because it's the change in velocity.
Yes, very good. So we have that at is the change in velocity. So at is dv by dt. And all relations we have developed before for constant acceleration were based on a equals dv by dt. So here, if at is constant, you can apply the same relations we have applied before for s, v, and so s is s0 plus v0t plus half at. So here it's at, put it here t, at, which is constant, times t squared. Okay. And if at is not constant, we go back to the differential relations and we integrate. Okay. And if if at constant also, we can use that v is equal to v0 plus at times t. And the relation independent of time, v square final equals v square initial plus 2at delta n. Never I use an here, or never I use total acceleration. I can use these equations only if at is constant. And of course, at ds will be equal to v dv, because at is dv by dt. Okay, now, as you know, to calculate the normal acceleration, we need the radius of curvature. This is why we will give you here a formula that will allow you to calculate the radius of curvature if you know the equation of your path. So if I give you an example, the path is expressed by y as a function of x, you can determine the radius of curvature at any point on your path using this formula. Okay? This formula will seem a little bit complex, but if you apply it, it's not hard. So what you do is you have y a function of x. You do the first derivative of y, and you calculate the second derivative of y. And the radius of curvature at any point on this curve is 1 plus the first derivative square and the whole term to the power 3 over 2 over the absolute value of the second derivative. Now we will do examples to see how to apply this form. Okay. So here, this is a first example. When the skier will reach point A along the parabolic path, he has a speed of 6 meters per second. which is increasing at 2 meters per second square. Determine the direction of his velocity and the direction and magnitude of his acceleration at this instant. Neglect the size of the skier in the calculation. Okay, so here, what we have is, we have a skier moving down on this path, and the path equation is given, y equals to 1 over 20 x². First, they want us to determine the direction of his velocity. Who will tell me how we will find the direction of the velocity? What should we do?
We should derive the equation of the plane, no, his trajectory.
No, look why no. Because this equation is y function of x, okay? And the velocity is derivative with respect to time. Do you have any idea about time here?
Oh, no,
We have to find
What we should find? What?
the
how-
tangent, the
very good,
equation of the
tangent.
tangent.
Exactly. Because velocity is always tangent to the path. So the velocity vector will be directed along the tangent to the equation line. Okay? And since I know the equation line, how to find the tangent of the angle? So here V is doing a certain angle, V is downward, and it's doing a certain angle with x-axis. This angle, which is theta, okay, can be calculated mathematically by doing what? This is the slope of my curve. How to find the slope of a curve? What should we do in math? What do? You derive the function. You say dy by dx. You say that tangent of theta, which is the slope of my curve, is dy over dx. So here in particular, I am interested at theta at point A. So I need to find dy by dx at A. So first I will find in general what is dy by dx. Then I will apply it at point A. So first, what is dy by dx? I have the function, which is 1 over 20x². If I derive it with respect to x, what do I get? I get 2 times x over 20. So it is equal to x over 10. This is my first step. Now, to find at A, if you look at the figure, you need to find x of A. From the figure, if you project A on, if you do the projection on x-axis, the coordinate of A is 10 meters. So now if you replace in your equation here, you can say that dy over dx at A is simply equal to xa over 10, x of A over 10, it's equal to 10 over 10 equals to 1. Okay, so if tangent theta equals 1, what will be angle theta? So theta,
45.
yes, exactly. So theta A is tangent minus 1 of 1, which is 45 degrees. So the angle, now we found the direction of velocity, and it's 45 degrees but downward. So you can just put your representation of velocity vector like this. It's doing an angle of 45 with the horizontal, and it's acting downward. Okay, so this is here, this is 45. Okay, now next step, for the velocity, I just need the direction because the magnitude is given. The speed is equal to 6 meters per second. So now I know everything about my velocity. Now as a next step, I want to find my acceleration. So here for acceleration, first, why here I should think about normal tangential coordinates? Because look, do I have any relation with time here? I don't know how x is varying with time. I don't know how y is varying with time. I just know the path. So when you just know the path, the best idea is to use the normal tangential coordinates. First, what did they say here? They gave you an important information. They say that the speed is increasing at 2 meters per second square. This represents what? This number. When they say the speed is increasing at 2 meters per second square.
Acceleration.
Which acceleration? Which component of acceleration represents the change in speed?
AT.
Tangential.
Tangential. So this represents AT. And here, because they said increasing, this means what? That AT is positive. Okay? Because look, always in normal tangential coordinates, V is always positive. We cannot have V negative in normal tangential coordinates. Why? Because UT always follows V. Okay? In normal tangential coordinates, so this is UT here. UT always follows the velocity. This is why V in normal tangential coordinate is always positive, not like IJ, not like in IJ K coordinates. Okay, so since V is always positive, V always positive in UT-UN frame. Okay, this is why when they say velocity increase, so when we have acceleration here, when we have acceleration, okay, what is the condition we said before for acceleration? Is that AT times V should be positive, okay? But since here V is always positive, so the condition for acceleration here is that AT should be positive. And if we have deceleration, then AT will be negative. Okay? So here, because they said the speed is increasing at 2 meters per second square, so AT is positive, equal here 2 plus 2. Now, we still need to find AN. So AT is directed along UT. We still need to find the AN component of acceleration. To find AN, we will use the formula. From the formula, what is AN? If you remember, it's V square over rho. Okay, it's V square over rho. Now, how to find here? We have the velocity. The velocity is equal to 6. How to find rho? What should we do? What should we do to find rho?
The previous formula.
Very good. We use the previous formula. Okay? The formula of rho we developed in the previous slide. Okay. So, now. Okay. What is the formula? If we go back to the formula here, we want to apply it. Okay? I will write it here. We have that rho is equal to, first I want to find, it's 1, rho is equal to, first it's equal to 1 plus dy over dx, okay, square, and the whole term to the power 3 over 2, so 1.5 to the power 3 over 2, which is 1.5, divided by the absolute, velocity, so divided by the absolute value of the second derivative, which is d square y by dx square. Okay. So now to be able to compute this term, okay, what should we do? We should find the first derivative and the second derivative. Okay. So here we have already calculated the first derivative. We said that dy by dx is x over 10. Okay. So and here at point A, to find the rho at A, we will replace in this formula dy by dx at A by 10. We still need to find the second derivative. The second derivative, since dy over dx is equal to x over 10, then if I derive this relation again with respect to x, so the second derivative, d square y with respect to dx square is equal to what? second derivative is 1 over 10. Okay, so now to find rho at A, all I have to do is to replace here dy by dx by 1 and the second derivative by 1 over 10. So I get that rho at A is equal to 1 plus 1 square, so it's 2, okay, to the power 1 over 5 over, because you are dividing by 1 over 10, so it's like times 10, okay? And in this way, you find the radius of curvature. Once I find my radius of curvature, then I can replace back into my equation. So here, let us see what the value of A will be. So replacing here, as you can see here, we do the calculation. We get that rho is 28.28. And now all I have to do is to say that my vector acceleration is equal to dv by dt ut plus v square over rho un. I get the components along ut and un. Okay. Now, if they ask you for the direction, so okay, yeah, 1 second. Okay. So now, if they ask you for the direction of acceleration, what should we do to find the direction of acceleration? So let us do a small figure together. Okay. Look, what we have here in general, when they ask about direction, we should give it with a certain reference that is known. So in general, when they talk about direction, we try to find the direction or with horizontal or with vertical, okay? Because u and ut are not fixed vectors, they are changing in location. This is why in general, we prefer to give direction with respect to a fixed direction, okay? So how to do the direction? First, we have the components of A along ut and un. So if you want to represent them, you have already, you know that if I consider this is the horizontal line, you already know the direction of ut, because ut, okay, look, ut is doing with the horizontal, as we have seen before, an angle of 45 degrees, okay? Now, the next step is un is perpendicular to ut. So if I want to present un, then un, I go from ut an angle of 90 degrees, okay? So the angle between un and the horizontal line here is 45 plus 90, is 135 degrees. Now, in un ut, I can easily represent my acceleration vector because I calculated the component, I have the component along ut, and I calculated the component along un. I have that the component along ut is 2. So here what I do, I draw, this is 80, and this is equal to 2 in magnitude. And un, I calculated that un is equal to 1.273. So this is my un. Now, if I know the components, I can draw the acceleration vector, and I can determine easily the angle it's doing, or with un or with ut. So for example here, if I want to find the angle of A with un, which is equal to phi, okay? This angle can be simply calculated using tangent, because tangent of phi is equal to this length here, which is equal to 80, over this length, which is equal to an. So I can say that phi is tangent minus 1 of 2 over 1.273. And I can calculate phi, okay? But phi is the angle with n, with un. And as I told you, in general, we prefer to give the angle with a known direction. So let us say we want to find the angle with the horizontal here. So this is my horizontal line. And I want to define the angle of my acceleration with this line, okay? If I want to give the angle with this line, as you can see in the figure, this angle here, this one, okay, is equal to phi, the whole angle, minus this one, okay, minus this one. This one is the angle between un and the horizontal. And the angle between UN and the horizontal is what? You can simply find it because here you have 45 and 90 and the whole angle is 180. So this angle will also be 45 degrees. Okay, so this angle here is 45 and the angle from UN to A is 57.5. So to find the angle between the acceleration and the horizontal, this one here, all you have to do is to do phi minus 45, and then you can define the direction of A with respect to the horizontal. So here, what you can do is, this is my horizontal. You present A like this. This is the direction of A. It's doing an angle of 12.5 with the horizontal, and it has as a magnitude a radical of 80 squared plus an squared equals to 2.37. Okay? Any question on this, how we found the direction?
Doctor, can you go back to the original figure, please?
Yes.
I want
This
to
one?
check something.
This one?
No, the original figure
Ah.
of the skier.
Yes, sure. Yes.
Okay, thank you.
Okay, another example. We have that the race car C travels around the horizontal circular track that has a radius of 90 meters. If the car increases its speed at a constant rate of 2.1 meter per second square, starting from rest, determine the time needed for it to reach an acceleration of 2.4 meter per second square. And what is the speed at this instant? Okay. So here we know the type of motion, it's a circle. When we have a circle, as we said, the radius of curvature will be constant, equal to the radius of the circle. Okay, so here always for a circle, you can directly say that the radius of curvature is 90 at any location. Okay, now they are saying that the car increases its speed at a constant rate of 2.1 meter per second square. So this represents what? The increase in speed. This is, as we said in the previous problem, this is 80. And since it's an increase in speed, so 80 is plus 2.1. Plus 2.1. Okay? Now, since my system starts from rest, so I can say that from this sentence, we can say that V0 is equal to 0. Determine the time needed for it to reach an acceleration of 2.4 meter per second square. This represents what? This is the total acceleration. So when they just talk about acceleration, this means it's the total acceleration of my particle. The total acceleration is given 2.4 and AT is given also. Okay, so we can determine what we want to find is what will be the speed when we reach this acceleration. Okay, so we will continue this together in the next in the session I will open now. Okay, so I will close this one and open a new session.